Today we're very happy to have Dr. Mike Hahn from Columbia University. He's in the astrophysics lab, and he's a research associate scientist there. And before that, he got his PhD degree in applied physics, also from Columbia, and then working as a postdoc in that astrophysics lab for a few years. And his research interest is in solar physics, and especially to conduct lab atomic physics measurement to better observe and understand the process on the sun. Mike? And because this is recorded, if you want to have your questions to be heard, you can come up here or ask me for Mike.
Okay, so thank you for inviting me to give this talk here. I'm going to talk about some observations that we've done about Alfvén wave heating and anisotropy in the solar corona. So these are kind of two somewhat separate topics, although they are related. The first half of my talk then will be about coronal heating by Alfvén wave damping. So there will be an introduction about why we want to study that. I'll describe our observations and the analysis that we did. And part of that analysis is that we need to account for a systematic effect from scattered light. So I'll describe how we did that. We measure the waves and the wave amplitude by studying the broadening of spectral lines. And the spectral lines are also broadened by the ion temperature. So there's thermal and non-thermal broadening. And I'll discuss how we try to separate those. And finally show our results. And then in the second half of the talk, I'll talk about anisotropy in a coronal hole measured near the sun. I'll give some motivation for why that's interesting and how that's related to waves. I'll describe our observations and methods for measuring this anisotropy, and then present the results for our temperature and non-thermal velocity, which are anisotropic with respect to the magnetic field direction, and also how you can do something similar to measure Doppler shifts. So to begin with the introduction to coronal heating by Alfvén wave damping. So we're interested in the coronal heating problem, which it's a fairly famous problem, and you're probably mostly familiar with it, but the problem is that in the photosphere, the temperature is a few thousand Kelvin, and then in the corona, the temperature goes up to 1,000,000 Kelvin, and you have this sharp transition region. So we want to know what is causing the energy to be transported from lower layers of the sun into the corona and making the corona so hot. In some ways, the problem should be easy because only 0.01% of the sun's energy output is required. And it's generally agreed that the energy source is the turbulent fluid motion in the outer convection zone. And somehow this mechanical energy is transferred into the corona and deposited as heat. So the jostling of the field lines by convection can give energy to the corona in two ways. One is by magnetic reconnection. It can move the field lines around into some configuration where they reconnect and release the energy stored in the field that way. And the other way is that this jostling can excite waves, and the waves travel up into the corona, and they carry some energy with them, and once they're in the corona, they dissipate, and the energy goes into heat. And this is kind of a controversial topic, which of these it is. So this is taken from a paper from 2010, which is asking the question, can the solar wind be driven by magnetic reconnection? And driving the solar wind is related to coronal heating. And their conclusion is that it is unlikely that magnetic reconnection is driving the solar wind. And the same year, there was this other paper that claims to demonstrate that the solar wind is not accelerated by waves. So which of these is the answer is an interesting question. One thing that the wave perspective has going for it is that we see a lot of waves in all parts of the sun. So here are some images of waves in the chromosphere. So what you're looking at here, this bright structure is a spicule, and I'll show a series of images at different times. This is from this paper by Depantu, 2007, and so you'll see this spicule kind of wiggling back and forth if you look at images taken at different times. And one way to really bring this out, and what they did is they plotted the intensity along this white line as a function of time and made this time distance plot, and you can see the spicule wiggling around, which suggests that there's a wave traveling along the spicule. You can also see waves in the corona. This is a movie taken with AIA from Scott McIntosh and other people. And so you can see that these field lines coming out of the surface of the sun are kind of swaying back and forth, so you see some evidence for waves there. And waves are also seen in the solar wind. So this is an old paper where they looked at, there was a spacecraft in the solar wind at the orbit of Venus. This is Mariner 5. And this plot is showing the magnetic field and the velocity perturbation as a function of time. So the time is in hours on the bottom. So these are kind of low-frequency waves. And each of these three plots corresponds to a different orthogonal direction on the spacecraft. Associated with each plot is two lines, and one of them represents the magnetic field and the other represents the velocity. And the fluctuations of the magnetic field and the velocity are in phase, which is suggestive of Alfvén waves. So waves are found throughout the corona and the solar wind. And if these waves are damped, then they can heat the plasma. The problem is that the simplest ways of damping waves, which would be collisions, that is viscosity and resistivity, damp the waves very slowly, only over length scales of about 3 solar radii. But the waves need to be dissipated below about 2 solar radii, because above that, the low density in the corona prevents the heat from being efficiently conducted downward and bringing the corona to a uniform temperature, and also because the solar wind is accelerating and eventually becomes supersonic, and once it's supersonic, the heat is advected away with the solar wind. So the heat has to happen at a low height. So we wanted to measure Alfvén waves and see whether they are damped at low heights in the corona. And so I'll describe the observation for doing that. We used data from the Extreme Ultraviolet Imaging Spectrometer, ICE, on Hinode. This is a picture of Hinode, and you can tell it's not a real picture because it's pointed away from the sun. And so Hinode was launched in 2006. It looks at the extreme ultraviolet wavelength bands. And what we're kind of using it for is that it has good spectral resolution. The spectral resolution is 22 milliangstroms per pixel. And then there's some instrumental broadening, but so it's good spectral resolution, and it looks along a slit. And so here are the slit positions for the observation we used. This is a coronal hole from April 2009, and the white lines here are showing the pointings of the ICE spectrometer slit. The background image is from EIT, and we didn't use any EIT data. I'm just using this to illustrate where the slit was. A reason for looking at a polar coronal hole is that they're sources of the fast solar wind. Here, this is data from the Ulysses spacecraft, which went in kind of a polar orbit around the sun. It kind of spiraled to high latitudes and then down to low latitudes and measured the solar wind velocity at each position. This is data from the solar wind plasma experiment on that spacecraft. And you can see that the coronal holes are at the poles, and that's where you have a fast wind. So the solar wind velocity here is the radial distance from the origin of the plot. And at lower latitudes, where the streamer and the quiet sun corona are, you have a slow solar wind. So coronal holes are the source of the fast wind, and that's where we had the ICE data from. So we took these 4 observations. They were about 30 minutes each, and we summed them together to have better statistics. And in total, they look up to a height of about 1.44 solar radii. And here's a typical part of the spectrum. So you have intensity versus wavelength, and you can see that there are all these different spectral lines. With ICE, they're mostly from iron and some silicon lines. And for a coronal hole, the temperature spans from something like iron 8 up to around iron 12. And so this is part of the spectrum. And then what we were interested in is the width of these lines. So we can zoom in on one of the lines. And again, you have intensity versus wavelength. And the histogram here is the data. And you can fit that with the Gaussian and extract the line width. Now this line width is proportional to the ion temperature and the non-thermal velocity. And both of these can be affected by waves. This equation is first assuming that we've subtracted off the instrumental width, which we've done. And the non-thermal velocity is related to waves because the mean square wave amplitude is twice the non-thermal velocity squared. And then the ion temperature can be affected by waves if there are high-frequency waves that resonate with the ions. So there could be ion cyclotron resonance heating. But what we'll mostly be interested in is this non-thermal velocity, because this shows us the wave amplitude. To know whether the waves are damped, we need to consider what the amplitude would look like if energy was conserved, that is, if the waves were not damped. So the wave energy flux goes as 2 times the mass density times the non-thermal velocity squared, so it's mv squared, and then it's propagating at the Alfvén speed. That's the group velocity of the waves. So this gives you a wave energy flux. And then the Alfvén speed is the magnetic field strength divided by the square root of the mass density. If the waves are undamped, then the amount of energy flux crossing some area A is a constant. So F times A is a constant. And then you can put this expression for the Alfvén speed in and see that F times A is proportional to density to the 1/2 times non-thermal velocity squared times magnetic field times the area. Now if you have a flux tube, then as the magnetic field lines get further apart, the magnetic field strength drops in proportion, and the cross-sectional area of the flux tube is increasing. So the magnetic field strength times the area of the flux tube is a constant. And that means that if this is a constant, and this is a constant, then the non-thermal velocity should go as density to the -1/4 power if the waves are undamped. That means that in the corona, if we're looking at larger and larger heights, then the density is decreasing, so we expect that the non-thermal velocity has to increase with this proportionality if the energy is conserved. So we will look for damping by seeing that the amplitudes do not follow this, this prediction. But before we can do that, we need to account for some systematic problems that could occur with the data, and that is mainly the scattered light. So scattered light is when the instrumental optics scatter emission from the bright solar disk onto the off-limb coronal spectrum, which is not quite as bright as the solar disk is. Line widths on the disk are narrower because you're looking into lower heights, so they're lower temperature regions, so the ion temperature is smaller, which means there's less thermal broadening. And then you're also looking to a higher density, so if the non-thermal velocity goes as density to the -1/4, if your density is higher, then the wave amplitudes will be smaller, so there's also less non-thermal broadening. So that makes the line width narrower on the disk. So if you're looking off the limb, and this scattered light makes up a large fraction of the total emission that you're observing, it can make the lines appear narrower than they actually are. So we need to address that issue, and to do that, we first determine the level of scattered light in the observation, and then subtract the stray light from the data by performing a double Gaussian fit. So here's an example of how we try to quantify the scattered light. And that is, we looked at the intensity of cool lines as a function of height. So these are oxygen 4, 5, and 6 intensity versus distance from the sun. And these are transition region lines, so in the corona they should be weak. And we see that at the edge of the sun the intensity drops very quickly. If you look at a large height, or above about 1.2 solar radii, and then average the intensity here, it turns out that the intensity there compared to the intensity on the disk is about 1/2 plus or minus 1%. So this is an estimate for the scattered light intensity as a fraction of the disk intensity. And we can get other... It's 0.5%, yes. So the fraction is 0.005, right? So the other, we used some other methods also to estimate the scattered light. We looked at there's a helium-2 line in the ice spectrum, and that's also a very cool line, so we can measure the intensity of that with height, and that also implies that at large heights the intensity of the line is less than 2% of the on-disk intensity. There were some observations where the moon passed in front of the sun, and there's this report by Ugarte-Ura where they tried to quantify the scattered light in ice using this eclipse observation. So part of the ice slit was looking at the place that was blocked by the moon, and part of it was looking at the sun, and so they could quantify how much scattered light there was in that situation, and they estimated that it was about 2% or maybe a little bit more. We can also look at the intensity versus height of lines that are formed at coronal temperatures, and they're dropping with height, with the scale height. And at some point we find that they also drop to 2% or less of the disk intensity, which implies that the scattered light fraction has to be less than this because some of this emission is real. So all of these different estimates are pointing towards the scattered light fraction being something like 2% of the disk intensity. So that's what we take as our scattered light intensity. We also did some tests for what if it were a little different, if it were 1% or 3%, and we find that our results are robust to this kind of uncertainty in what the scattered light intensity is. So then we can try to remove the scattered light from the data by using double Gaussian fits. So here is an iron 9 line. This is at a large height where scattered light makes up more of the intensity than it does in most of our data, but this is to illustrate. And this dotted line here is showing our model stray light profile. So this stray light profile uses the measured on-disk line width and the measured on-disk centroid position and 2% of the on-disk intensity. And then we fit the real emission by adding another Gaussian to this that has free parameters and allowing the total of these two Gaussians to fit the data. So here the dashed line is the Gaussian that represents the real emission in the corona. So now we've removed the scattered light from the data, and now we need to separate the thermal broadening from the non-thermal broadening. So the total line width depends on the ion temperature and the non-thermal velocity, which you could think of as the thermal velocity plus the non-thermal velocity. And we'll express the line width as an effective velocity. So the way to separate these is to make a couple of assumptions. And the first assumption is that we'll assume that the ion temperature isn't changing with height. So that means any changes in the line width are due only to changes in the non-thermal velocity. This is reasonable as long as you look at low heights in the corona, below around 1.1 solar radii. And the reason is, if you compare the time scale for ion heating versus the time scale for collisions between ions and protons. And that's what's shown here. So this is from a paper by Landy and Cranmer, and on the y-axis you have the time scale, and on the x-axis is distance above the sun. Here they're using, I usually have the plots that go from the center of the sun out, but they're measuring from the surface of the sun out, so it's just our sun minus 1. And the dashed line here is the collisional timescale between ions and protons. And so that's a cooling timescale because the protons are observed not to be strongly heated. They maintain kind of a constant temperature in the corona up to large heights. So collisions between the protons and the ions will cool the ions, even if the ions are being heated. So, so that's a cooling mechanism. And this solid line is a heating timescale that they, from this kind of empirical model that they were reporting in this paper. And what you can see is that at low heights, the cooling timescale is faster than the heating timescale. So that means if you stick to such low heights, the ion temperature shouldn't be increasing very much. Of course, at larger heights, around above about 1.2 solar radii, the heating timescale becomes less than the collisional cooling timescale, and then the ion temperature can increase a lot. And then in between, it's kind of doing something in the middle. So if we stick to low heights, we can use this first assumption that the ion temperature is roughly constant with height. And the second assumption we'll make is that at the lowest heights, we'll assume that the waves are undamped. And this is based on previous observations at very low heights in the corona. So if you look only up to around 1.1 solar radii, then here I'm plotting the effective velocity versus distance for an iron 9 line. And you see that here the solid line is some data, and the dashed line is the density to the -1/4 power dependence. And up to those heights, it follows this trend pretty well. And similar results have been found by many other people. So there are papers by Banerjee, Dolan, Solomon, Doyle, and others that show that at low heights, this density to the -1/4 dependence is followed. In that case, any change in the non-thermal velocity depends on the density, and we can measure the density independently. So we measured the density using an iron 9 line ratio. So this is just the intensity ratio of two density-sensitive iron 9 lines. This is density versus distance from the sun, and the points are our data. And we can extrapolate that to larger heights using a scale height fit. And then we also want to use this to larger heights, and so that's why we have done this extrapolation. But the scale height fit might not be totally accurate at large heights because you have the solar wind is accelerating, So the scale height is for a hydrostatic equilibrium, and the corona is not really hydrostatic. So we also included this empirical function from white light measurements and normalized that to match the data. And you can see that in the height range we're interested in here, the difference isn't very great. We used the more accurate empirical function in the rest of the analysis, though. So if we take these two assumptions and we put them together, then the line width can be fit by this function. So this is a function that depends on the thermal velocity, which is a constant with height, and the non-thermal velocity at some particular point, and these will both be free parameters. And then the variation in the non-thermal velocity is determined by this density ratio, which we have measured. So we have this equation that we can fit to the data and then determine the thermal and the non-thermal velocity. So here is such a fit. So we fit the data up to 1.12 solar radii, and the solid line is the fit, and the points are the data. And this is for an iron 11 line. And so you can see that it matches the data here. And so we extrapolate a thermal velocity of 25.8 kilometers per second and a non-thermal velocity of 32.2 kilometers per second. And I've also plotted the data up to larger heights. Of course, at some point it stops matching this fit because the waves are damped. So to really find out how much they're damped, we want to extend our non-thermal velocity measurements to larger heights. So for the fit, we used up to 1.12 solar radii, but we want to use our full data that goes to 1.44 solar radii. And the way we'll extend is to assume that the ion temperature remains constant. Now, I said a little while ago that the ion temperature doesn't remain constant because eventually the heating will become stronger than the cooling. And we don't really know how much the ion temperature is increasing because we don't have an independent measurement of it. But it should be constant up to some point, and then it will start increasing. So in reality, the ion temperature is increasing. But this isn't too much of a problem because in deriving the non-thermal velocity, that would mean that at large heights, we're not subtracting enough thermal velocity. So if we're looking for wave damping, that means we're actually underestimating the amount of damping. So if we're not subtracting enough thermal velocity and we're underestimating the damping, then the damping that we see is even more likely to be real. There's actually more damping than we find. So now I'll show you the results. So here is non-thermal velocity versus height for several different lines, which are shown by the different colored points. And the density to the -1/4 trend is for undamped waves is the dashed line here. And this solid line is the average non-thermal velocity. And you can see that around about 1.15 solar radii or so, the waves are starting to be damped. One other thing that I want to point out about this plot is that we've derived these non-thermal velocities by subtracting off the thermal velocity. And the thermal velocity is allowed to be different for each ion species. But we still get the same non-thermal velocity for all of the ions. And that's an indication that this method works because you expect for waves to have the same non-thermal velocity because it's moving the entire fluid and all of the different ion species at the same time. So all of the ions should be affected by the low frequency waves in the same way. So if we have the non-thermal velocity, then we can estimate the energy flux in the waves. So these are the equations from before. And we need to know the mass density, and we can determine that from the electron density, and then it'll be 1.15 times the proton mass times the electron density. Where this 1.15 comes from assuming 5% helium, so it's a little bit more than 1. And then for the magnetic field strength, we need that to get the Alfvén speed. So for that, we use an empirical model which relates the magnetic field strength to an area expansion factor. So what they did to get this empirical model was they just looked at how the field lines separate with height above a coronal hole and extracted from that the area expansion. And the magnetic field needs to be normalized to some value at the base of the corona, and we took that value to be 7.3 Gauss, plus or minus 1 Gauss as an estimate of the error on that. And then here is the wave energy flux. So energy flux versus distance from the sun, and you can see that the energy flux is always decreasing, and that's because the area is increasing. So the waves are being spread out over more and more area. We can correct for that by multiplying by this expansion factor. And then on this plot, a horizontal line would show you undamped waves. And this solid line is a fit to this result. So it's the fit is set to be a constant at some level, and then there's a point where it becomes an exponential decay, and this point is allowed to be a free parameter, and then there's some exponential characteristic length scale that's also fit. And what we find from this kind of fit function is that at the base of the corona, 6.7 times 10 to the 5 ergs per centimeter squared per second of energy is injected. And then the waves start to be damped at around 1.12 solar radii. And they're damped over a length scale of 0.18 solar radii. Now, some people who make models of wave damping might want to use a time scale and have them damping in time rather than in space, and we can convert to a time scale using the Alfvén speed, in which case this damping length becomes a damping time of about 68 seconds. So then, the classical estimate of the amount of energy needed to heat a coronal hole and accelerate the fast solar wind is 8 times 10 to the 5 ergs per centimeter squared per second. But during the 2007 solar minimum, the solar wind was observed to be somewhat weaker than in previous minima. It was less dense and a little bit slower. And so it's been estimated that about 25% less energy would be needed to accelerate that solar wind, which would suggest that only about 6 times 10 to the 5 ergs per centimeter squared per second of energy is required to heat the corona then. And we've measured 6.7. So we can conclude that the waves carry and dissipate enough energy at low enough heights in the corona to heat coronal holes and accelerate the fast solar wind. So now I want to kind of switch topics a little bit and talk about measuring anisotropy in a coronal hole near the sun. So this is not directly related to the wave damping, but it does tell you something about the waves, because the anisotropy arises, there's anisotropy in the ion temperature, which can be due to ion cyclotron resonance heating or stochastic heating by turbulence, and that depends on having some high frequency waves in there, and that might be an indication that somehow these low frequency waves we're observing decay into high frequency waves through some turbulent cascade. And also the signatures of waves are anisotropic, depending on whether you have Alfvén waves or magnetosonic waves. So I'll explain this a little more in the motivation, but this is the next topic I want to talk about, and I'll start with the motivation. So in the solar wind, the ion temperatures are anisotropic, and here is a plot of the proton velocity distribution in the solar wind. This plot needs a little bit of explanation. So this is from data taken at 0.54 AU by some spacecraft, and the x-axis is the solar wind velocity vector, and the green line here is showing the magnetic field vector. And this cut was made in the plane in which the velocity and the magnetic field were in the same plane. Now, it's got kind of a funny shape out here, and that's because these dashed lines are showing out in the tails of the distribution. If you look in the core of the distribution, the shape is a bit more regular. It looks like an oval. And what you can see is that the velocity spread along the magnetic field is smaller than the velocity spread across the magnetic field. So that's saying that the parallel proton temperature is smaller than the perpendicular proton temperature. And in the solar wind, the perpendicular ion temperature and the perpendicular is greater than the parallel ion temperature. This is likely from ion cyclotron resonance heating or heating by turbulence, which tends to kick the ions perpendicular to the magnetic field. Wave fluctuations are also anisotropic. If you have Alfvén waves, they cause a velocity perturbation perpendicular to the magnetic field. Or if you have a magnetosonic wave, then this is a wave that travels along the magnetic field, but it causes a compression and has a velocity perturbation that's also in the same direction as the magnetic field. So that causes a parallel non-thermal velocity. So we would like to be able to measure Alfvén waves and magnetosonic waves in the low corona, and also tell whether the ion temperatures are anisotropic there. So we've already shown that we've measured Alfvén waves in the corona, and the reason is because observations of the corona tend to see perpendicular. So here is a magnetic field model of the corona for an observation that I'm going to show. This is a potential field source surface model. And if you just imagine your spacecraft out here, then your line of sight is tending to go across the magnetic fields. So you're seeing perpendicular line broadening, and so that's telling you the perpendicular temperature and the perpendicular non-thermal velocity. So it's telling you about Alfvén waves. So we want to try and measure the parallel component in the low corona, which hasn't been measured before. So to do that, we used this observation of a coronal hole, which is on the solar disk and at a low latitude. So this background image is an EIT image in iron 12, and then this box here is showing the ice data that we used for our observation. We can zoom in on that, and then here is the intensity of the iron 12 line seen by ice, and this is a raster, and I've binned it up into fairly large spatial bins, and the dots in each of those bins represents the ones that we chose for the analysis. So we wanted to avoid any kind of structure in the coronal hole and get as a kind of pure coronal hole. So we avoid this quiet sun down here, and there are some little bright points, but because of the large spatial binning, it could be that we still have a little bit of contamination in there, and you'll see that in the scatter. Yes?
Are you saying that you're only analyzing those points that you differentially also analyze the other ones?
We looked briefly at the other ones for some things, but for what I'm going to do, we only analyze these points. The reason is because I want to use the magnetic field to, and I'll show on the next slide, is that we want to measure things with respect to the magnetic field, and we want the magnetic field to be open for this. And so if you have this bright point, that's probably where there's closed field and it's being heated down there. So it doesn't make sense to measure things with respect to the magnetic field direction.
But nevertheless, it is a null test. Test in a null hypothesis.
Yes, that's a good point. So okay, so here is the potential field source surface model for the time of this observation, and our observation corresponds to about where this orange box is. So what I'm going to do then is trace the magnetic field line coming out of the base of each of these, coming out of the center of each of these spatial bins, and trace that magnetic field, and you'll see that on this slide, and I've rotated it a bit to the right, about 50 degrees, to emphasize the changing angle of the magnetic field. So then if you're looking towards the towards low latitudes, towards the equator, then the line of sight tends to be along the magnetic field here, so you're seeing more the parallel direction. And if you looked towards the pole here, then you tend to be looking across the magnetic field, so you're looking perpendicular. And you can quantify the angle between the line of sight and the magnetic field, and we'll call that angle alpha here. And let's call the angle of the line of sight z hat and the angle of the magnetic field b hat, and then your alpha is just the inverse cosine of b hat dot z hat. So you can derive this this angle between the line of sight and the magnetic field in a straightforward way from the potential field model. And then we can use that to measure the temperatures and non-thermal velocities. So what we've done is, so here we have the line width expressed as an effective velocity versus the angle alpha. And so 0 degrees is when you're looking parallel to the field. So over here on this side of the plot, at 0 degrees, is the parallel line width. And at 90 degrees is when you're looking perpendicular to the field, so this is the perpendicular line width over here. And we have data in the middle, so we fit it with a function like this. So this is the parallel line width times the cosine of the angle squared plus the perpendicular line width times the sine of the angle squared, and you can fit such a function. Now, as I said, there's some scatter here, and we believe that this is from some other structures in the rather large spatial bins we're using. We use those large spatial bins to have good statistics for finding the line widths, but they do cause a little scatter. So part of this is based on the belief that this is the correct kind of function to fit this data with. So then if we take just the perpendicular component, and that's determined by the perpendicular ion temperature and the perpendicular non-thermal velocity, and we expect the perpendicular ion temperature to vary to vary by ion species in a way that depends on the charge to mass ratio, because we expect it to be due to ion cyclotron resonance heating, and the different ions will have different ion cyclotron resonance frequencies. So we need some way to separate the thermal and the non-thermal broadening here, but we can't use the same trick that we did before because we don't have height information, because we're looking down onto the solar disk. So we're integrating along different heights, even though we're probably concentrated at the lowest heights where the density is largest. But what we can do is get bounds for the ion temperature and the non-thermal velocity. To get these bounds, we'll assume that all of the ions have the same non-thermal velocity. So the non-thermal velocity is due to some wave and it's moving the whole fluid. So all of the ions will be affected in the same way. Then we can get an upper bound on the ion temperature by assuming that the non-thermal velocity is 0. So if the non-thermal velocity is 0, then all of the broadening is thermal broadening, so that gives you an upper bound on the ion temperature. To get the lower bound, we'll assume that the ion temperature has to be at least as large as the electron temperature. At some point, low in the corona, the ions and the electrons were collisionally coupled, and so they had the same temperature. And then as the height is increasing, then the ions are being heated, then the ion temperature is increasing, so we expect the ions to be at least as hot as the electrons are. And that gives a lower bound. And so here is perpendicular ion temperature versus charge to mass ratio. And the ions that they come from are labeled along the top here. So you have iron 8 through 12, iron 13, and some silicon lines, some magnesium. But the main thing to see is that at low charge to mass ratios, you have a relatively high ion temperature, and then that drops and maybe levels off as the charge to mass ratio is increasing. And this is characteristic of some models of ion cyclotron resonance heating, and it's also what is seen in Alfvén measurements. So the Alfvén measurements are looking mostly in the perpendicular direction, and they see this kind of thing before. So that we see it here is an indication that the analysis works fairly well. And we also measure a perpendicular non-thermal velocity of 28.3 kilometers per second at these heights, which is consistent with the Alfvén data in at low heights. So that's. Oh yeah, we've tried to always for this analysis use unblended lines. So yeah. So that was considered. So we didn't use any lines that were known to have blends. I mean, perhaps lines have blends that we don't know about, but those were removed. So then we can go on to the parallel direction, which is the direction that hasn't been measured before. In the parallel direction, we find that all of our data is consistent with the ions all having the same parallel ion temperature, which is best fit by 1.8 million Kelvin. And in this plot, what I'm showing is the parallel ion temperature versus the log of the formation temperature. So this formation temperature represents the electron temperature at which each ion species is most abundant in ionization equilibrium. So something with a low formation temperature would be something like iron 8. Something with a high formation temperature would be like iron 12 or 13. So this is being plotted in terms of formation temperature here. And this solid line is showing formation temperature equal to ion temperature. And the reason for this plot is to emphasize that the ion temperature seems to be generally larger than the electron temperature at which the ions are formed. And since all of the ions have the same temperature, that's also interesting, because it suggests that the ions are in equilibrium with the protons. So why could the ions all have the same temperature? One reason is that every ion species happens to be heated in the same way to exactly the same temperature, and this seems kind of unlikely. And then more likely is that they're in equilibrium, but they can't really be in equilibrium with each other because they're minor ions. There's not very many of them, so they don't experience many collisions among themselves, but they do collide a lot with the protons. So it could be that this 1.8 million Kelvin is a value for the proton temperature at a low height in the corona. So that's interesting. So we can compare that to other measurements of the proton temperature. So we believe, based on the density that we infer in the observation, even though we're integrating along a line of sight and we're seeing all different heights, that the average height we're looking at is around 1.02 to 1.05 solar radii. And that's based on the density that we measure, which is about 2 times 10 to the 8 per cubic centimeter, which for a coronal hole corresponds to this kind of height range. And so here is a plot of different temperatures. This is from this Landy and Kramer paper. And the red points are showing different measurements of the proton temperature. So at a couple of solar radii, you have measurements from UVCS, and then there are some, I think these are from Lyman alpha measurements in the transition region at a temperature of about 100,000 Kelvin. And our measurement falls somewhere in here at a temperature of 1.8 million Kelvin. And so this seems to show that there's this sharp proton temperature transition region, and after that the proton temperature stays kind of constant with height. And the other things shown in this plot are kind of typical electron temperatures in the corona, and then this average plasma temperature model from this paper. But the point I wanted to make was that just to show the different proton temperature measurements and how ours fits in with the existing knowledge about that. So we measured the proton temperature, and at the same time you get a value for the parallel non-thermal velocity, which is a measure of the sonic wave amplitudes. So we determined that the parallel non-thermal velocity was about 12.6 kilometers per second. Now, if this is due to magnetosonic waves, then those waves, they're also compressive. So people have tried to measure those using intensity fluctuations in the corona, and based on those measurements, they've inferred a fluctuation of about, that corresponds to an amplitude of 10 kilometers per second. So what we measure for sonic wave amplitudes also seems to agree with these intensity fluctuation measurements. So that's kind of a verification that, that our analysis in the parallel direction is reasonable. And finally, I'd like to talk about Doppler shifts, and you can do something similar using this angle between the line of sight of the magnetic field and the magnetic field to measure Doppler shifts. So you probably know that a Doppler shift is the shift of the wavelength from the rest wavelength and is proportional to the line of sight velocity. The problem with measuring Doppler shifts is that this rest wavelength is the rest wavelength on the detector. So if you have a detector that's on a spacecraft, then you could have calibration issues, and it could also be moving relative to the sun. So this rest wavelength is not necessarily the laboratory wavelength for the transition. There are some different ways people have tried to use to measure these Doppler shifts. One way is that you can put in a calibration lamp on board your satellite and always calibrate your spectrometer, but most satellites don't do this. Another way you could do it is to use a chromospheric line for the rest wavelength and just assume that that line is stationary, and then you can measure all the other wavelengths with respect to that line and determine the Doppler shift that way. But this means that you have to assume that this chromospheric line isn't moving, and that's not very satisfying, and it could cause errors if, for example, there are flows in the chromosphere causing a Doppler shift. Another thing that you could do would be to use an off-limb part of the observation for the rest wavelength. So in the off-limb part of the observation, you're looking perpendicular to the field lines. And in the corona, the magnetic forces are stronger than the fluid forces, so you expect that the fluid isn't traveling across the field lines. It would be traveling along the field lines. So in that case, if you're looking perpendicular to the magnetic field, there shouldn't be a flow in your direction. The problem with this method is that you're assuming that the line of sight off of the disk is really exactly perpendicular to your line of sight, and it could be that it's inclined a little bit towards you or a little bit away from you. But we can use a method similar to this last one because we actually know the direction of the magnetic field to the line of sight from the magnetic field model. So we have, if we substitute for the line of sight velocity the parallel component of the flow velocity times the cosine of this angle plus the perpendicular component times the sine of the angle, then you have this expression for the Doppler shift. Now, if there's no flow transverse to the magnetic field, then you can get rid of this term. And then you have the Doppler shift is linear in the cosine of alpha. So here is the wavelength measured for an iron 9 line versus the cosine of the angle in our observation. So at cosine of the angle is 0. That means you're looking perpendicular to the magnetic field. So this is telling you the rest wavelength over here. And at cosine of alpha equals 1, this is when you're looking along the field. So this is when the Doppler shift is maximized with respect to the angle that you're looking at it with. And from this, we can derive the rest wavelength and the flow velocity. In this case, the rest wavelength was this, which agrees within the uncertainties with laboratory wavelengths. and we find a parallel outflow velocity of 5.9 kilometers per second. And then we can measure this for different lines and different ion species and make a plot like this. So this is outflow velocity versus formation temperature, which again is the electron temperature at which the ions is formed. And at coronal temperatures, which is around 5.8 to 6, around 1,000,000 Kelvin, we find an outflow velocity of around 5 kilometers per second. At lower formation temperatures, we see that the outflow velocity is increasing with temperature. One explanation for this is that these lower temperatures means that you're looking into lower and lower layers of the solar atmosphere, so this could be showing the initial acceleration of the plasma forming the initial acceleration of the solar wind. Another possible explanation is just that we have these large spatial bins and we have some cooler structures in there that have less flow velocity. And then at high temperatures, we see kind of a small outflow also, but these high temperatures are higher than kind of a reasonable coronal hole temperature, so we suspect that these are from contamination from some other hot structures in the coronal hole that aren't really these open field lines in the coronal hole. So this is likely a systematic from our large binning. So then, in conclusion, in the first half of the talk, I try to show you that Alfvén waves carry and dissipate enough energy at low enough heights to heat coronal holes and accelerate the fast solar wind. And then in the second part, we showed a new method to measure anisotropy by combining spectroscopic observations with a magnetic field model. Now this has left a number of open questions. For example, why are the waves damped? And can the waves heat other structures? Both parts of this talk have focused on coronal holes, and we'd like to know, can waves also heat the quiet sun corona, for instance? Why is it that the protons are hotter than the electrons at very low heights in the corona, as indicated by the parallel ion temperature measurements? And we also saw that the ions are heated anisotropically. So in the perpendicular direction, there was this charge to mass ratio dependence, but in the parallel direction, they all have the same temperature, which shows that the ions are heated anisotropically, which suggests that there are high-frequency waves that are resonant with the ions, or turbulence at low heights in the corona. So what is the source of this turbulence in these high-frequency waves? And just before concluding, I'd like to acknowledge Daniel Savin at Columbia, with whom I work, Enrico Landi, our collaborator at the University of Michigan, and our support from NSF Shine. So thank you for your attention.
Questions for Mike?
So I'm not a solar physicist, so I can ask dumb questions here. You're assuming that the Alfvén waves, the reduction in amplitude is due to damping. Mm-hmm. How can you rule out reflection, downward reflection?
Yeah, so it could also be reflection. So it could be that the waves are trapped at low heights somehow. But yeah, so we're kind of considering that to be part of damping. If the waves get trapped there, then they can't get out, and they're going to deposit their energy at the low heights. So yeah, even though it's different,
So are you saying most of the Alfvén wave energy flux are dissipated already by what height? 1.2? Or 1.5? So they're all damped in low corona?
Yeah. Yes, it looks like most of the energy is damped at a low height. So here you have. So here it looks like a lot of the energy is going away. Now, it could be there's still about 10 to the 5 ergs per centimeter squared per second here, and maybe there's maybe still enough left to keep going out, because we know that there are Alfvén waves in the solar wind.
Yeah, I read this paper by Agel, Lear. You know, they study where the height at which the energy deposition takes place. Mm-hmm. They found if the energy deposition is mostly happening at low corona, you get mass flux rather than speed. If you deposit it beyond, at higher height, beyond the Alfvénic points, then you get mostly acceleration. So it's the height at which it's, I just read that paper. It seems it's important where it is deposited, and then it will affect the results of the wind speed versus the mass flux.
Mm-hmm. Yeah.
So is this, how does this relate to the result?
I think, yes, I've heard something about this too, and I think that what I've read, you need the amount that you need above the sonic point to accelerate the solar wind to the fast speeds that we see is about 10 to the 5 ergs per centimeter squared per second. So if the damping is really about like this and doesn't continue, maybe if this levels out or something, then there would still be enough to get a fast solar wind out of this. But I mean, this is really at the limit of what we can measure, and so we don't know. But yeah.
Hey Mike,
Hi.
do you want to explain to the folks in the room about how a 5 kilometer per second apparent parallel flow can become 600 kilometers a second? Even though you've damped a whole bunch of things?
How the 5 kilometer
5 kilometers a second isn't 600 kilometers a second, which is the nominal escape speed.
Well, no, but this is looking at a very low height of around just above at around 1.02 to 1.05 solar radii, and so I think that a low flow speed at that point is reasonable. If so part of the way to estimate how the flow is accelerated is mass conservation, and so if you have the expansion is going to cause a lot of acceleration. So if you start off with a high density at 5 kilometers per second, and then the density is dropping and the area is expanding, then this is going to cause some acceleration. And then you're also inputting more energy with heating at larger heights. So I think that, I mean, the solar wind doesn't start off going 600 kilometers per second. It is accelerated somewhere between, I think somewhere at a couple of tenths of a solar radii above the corona is where most of the acceleration takes place. For the expansion of the field lines?
In general expands on the whole, but do these clusters itself expand? I mean, these structures are very fine on which the waves occur. You don't see them out at the field of view of the AIA, which is 1.25 solar radii.
Mm-hmm.
You don't see expansion. So where's the expansion coming from? You don't. What I'm trying to say is I don't think you need expansion of field lines to accelerate the light.
Okay.
I just don't. It's not a nozzle effect, right? That's the whole premise of expansion factors in Langevin, the RG solar wind models, is that you invoke some arbitrary expansion factor to match what you see at 1 AU, based on a PFSS model or whatever. I'm not sure that that's physically consistent with what we see. But if it model works, it's a model.
Yeah, but if we have the solar wind also can't start off at 600 kilometers per second because we don't observe that.
No, I'm not saying that it does. At some point it picks up speed. But it's very unlikely that it picks up speed from 5 kilometers per second.
Thanks for a provocative talk. I think you tried to tie together a bunch of different data which sort of look like an almost credible picture of what's happening in these things.
Almost credible is what I was going for. Thank you.
Yeah. So I just had a couple of thoughts. Your two parts of the talk. The first comment I want to make is that you're combining essentially a fluid kind of interpretation with a kinetic kind of interpretation by looking at these two aspects. The ion temperatures, etc., are all kinetic descriptions, and you allow that freedom to have perpendicular versus parallel ones in the latter part of your talk. So while I believe that, below a certain height one should treat the whole thing as a fluid because of the collision times, as you point out, are very short. I want to ask a question. That is, how secure are you in the thought that there is definitive evidence, and it's not necessarily your work, but definitive evidence that we have genuine fluid-like behavior, namely all the turbulent velocities for all ions of all charge-to-mass ratios of all masses that you can possibly observe are really fluids? And then the second part is, in other words, do we have a fully collisionally coupled plasma low down. I think we should have. And then the other part is, well, there's a sub-part to that, and that is, I noticed that your velocities in the second part of the talk, the widths were very much narrower by a factor of almost 2. So I think in the first part of your talk, when you look above the limb, you're looking at a lot of flow velocity as well, not just line widths. What you assign to a line width is not the local wave power alone, it's also line of sight along field lines that are both along the line of sight, pointing have a component along the line of sight due to the expansion of the gas. Mm-hmm. So I think that means that this estimate of the energy is too big.
So
if you allow for real expansion of the gas there.
So in the second part of the talk, you're talking about...
I'm not making myself clear to myself even at the moment, so... But yeah...
So you're talking about here, I have 28.3 kilometers per second or so.
Sure, yeah.
And this seems smaller than before where I had
right,
30-something kilometers per second.
No,
yes.
40 or 50, I thought.
Well, that's also the thermal plus the non-thermal, right?
Okay.
So if... So this non-thermal velocity is smaller than the non-thermal velocity that I showed in the first half of the talk. And that's because here we're looking down into lower heights. If you were to correct for the fact that the density is larger here, then this would come out to be like 35 kilometers per second. So that can be corrected by just assuming that the waves are undamped in this density to the -1/4 dependence. As for the ion temperature being also a little bit smaller than in the off-limb data, yeah, this trend is similar to what you would see off-limb, but yes, the magnitude here is smaller, and this could also be because you're looking at lower heights where it's denser and there's more collisions. Collisions between the ions and the protons would tend to cool them. So we tried to estimate how much this flow in the coronal hole could broaden the lines. And I think we assumed 10 kilometers per second outflow at like 1.1 solar radii, or maybe 15 kilometers per second. But it came from this some empirical model of what the outflow velocity should be. And we estimated actually that this doesn't create very much broadening because as you look along the line of sight, the densest part is the part that's closest to the sun, and everything is dropping off with a scale height. And if you consider the intensity, then it's dropping off with half the scale height of the density. So you're really concentrated at the part that's at the height closest to the sun, and everything else is contributing exponentially less as you go away. So we're concentrated at the height that is kind of the nominal transverse height from the sun, and it doesn't appear like this is really causing very much broadening. I think we estimated 1 or 2 kilometers per second was due to that, but it was a small fraction of the total line width that we measured.
But have you, the question I really wanted to ask was, ideally you'd want to measure hydrogen, helium, carbon, nitrogen, oxygen, fluorine, neon, you name it, go through the periodic table. Yeah. And here you've got elements that are all of sort of the same mass, yeah, within a factor of a couple. So how sure are you, how secure are you in the knowledge that when you observe a line width, you can interpret it in terms of, you can genuinely find things on the kinetic scales versus the fluid scales in terms of the distribution functions of all those particles, because that's critical. Mm-hmm. I mean, should we take seriously, do we have to take seriously the fact that the ion temperatures that people have found are different in the parallel and perpendicular direction from remote sensing? I'm not talking about the Helios emission and stuff like that. I'm talking about remote sensing. I've always wondered about that.
I'm not aware of other measurements of the parallel temperature from remote sensing, but
UVCS is what I'm talking about.
Oh yes, but they used yeah, they used the resonance scattering, I think, for that. So they also have some kind of bound. So I think that this kind of analysis here seems to me to be pretty robust. I mean, we're getting an upper and a lower bound by assuming that this non-thermal velocity is 0 or the ion temperature is greater than the electron temperature. So really the main assumption here would be that all of the ions have the same non-thermal velocity. So this is where this distinction, I guess, between fluids and kinetic, this comes into this assumption. And I think that this seems reasonable, because if you have like a turbulent cascade, then most of the energy is going to be at the low frequencies. And at the low frequencies, all of the ions have time to react to the change in the wave fields in the same way. So if you make a distinction, I think, between the low frequencies and the high frequencies like this here, I think it seems reasonable, although I guess it depends also on how detailed you want to be with your fluid versus kinetic model. I mean, for just getting upper and lower bounds, it seems fine, but if you wanted to do something more sophisticated, maybe there are differences. I mean, you could also have coronal heating by like kind of like these exospheric models, that there's a tail to the electron velocity distribution or something, which would mean that kinetics is much more important than fluids, which would be assume everything is Maxwellian. So I don't know about that.
It seems that from the energy flux you just showed that there's a very well-defined boundary at 1.15. Is there any physical significance for that altitude?
So
Yeah.
you're talking about this here.
Yeah, if we look at
Yeah,
it.
so it is interesting, I think, because, well, for one thing, this is kind of a very artificial function to use. I mean, we have no reason to believe that it actually is constant and then starts decaying. I mean, maybe there's some kind of function that describes the decay of a wave, like maybe this would look a little bit more like a Gaussian or something. And so that it could be that it's kind of decaying a little bit over here, and then just as it's gradually speeding up, this function makes it look like there's a knee. It could also be that that it is due to reflection, and that this is where the reflection starts to become strong.
What scale height, in terms of scale height, what is 1.15 about the surface?
In terms of scale height, so for a million Kelvin, I think the scale height is 0.07, what, 0.08, 0.9, okay.
What is the Alfvén velocity?
It's about it's changing a little bit. It starts off at about 1,000 kilometers per second, and it's increasing somewhere in here to 2,000 kilometers per second.
Okay, no more questions. Let's thank Mike again.
Thank you.